So Lionel started to speak about the structure of the material, especially at small scales. You evocated thin films. It will be the subject of sessions 2 and 3, where we will see what metal give at a very small scale. But here we continue with macroscopic structuration of the metal, and we will see the influence of the shape on the color of the metals. So let's consider a flat mirror, and as we have understood from what Lionel has said, so imagine that you look at the mirror from one direction, and what you see is the ray that comes from the regular direction. So we have a radiance here that is reflected here, and the radiance is just multiplied by the Fresnel reflectance, which depends on angle and on polarization and on wavelength. So a way to feature into one plane what is the spectral reflectance or the color from every angle is to map. It is a classical mapping technique that was introduced for Earth at the beginning, so the Lambert's equal area map. So every direction is represented at one point. What is interesting is that it is well adapted to radiance representations. And let's see what it gives for different materials. If you have a glass, say glass mirror, a glass air interface, we retrieve, so normal incidence is at the center, and then you go to grazing angle. And as Lionel said, with the dielectric like a glass, the reflection at normal incidence observation is low. It is 4%. And at grazing angle, it is 100%. All the light is reflected. And he also said that with metal, the reflectance is much higher. So here we are in the case of pure gold, and we have the yellowish aspect of gold that is visible at normal incidence. And as every other material, at grazing angle, 100% of the light is reflected for all wavelengths, so it is white. Here, silver is very highly reflective. I don't know if the projector renders the slightly yellowish aspect of silver, and the copper is somehow pinkish, as we know. Aluminum reflects 80% of the light at almost all angles. Of course, 100% of the light. And here, silicon, which is a semiconductor. The question now is the question of color. So in these maps, obviously, the spectral reflectances have been transformed into RGB values. So please admit that the spectral reflectance, the conversion between spectral reflectance to RGB values is with a standard method, which is not, of course, accurate because it depends on the spectral property of the projector and so on. But it is a standard method that is used in the computer graphics. But now, if we ask the question, what is the color of a mirror? The question is not easy because actually what we look when we look at the mirror, we don't look at the mirror in itself. We look the scene that is reflected. Okay, so when I look at me in the mirror, I look at the color of my skin, not the color of the mirror itself. And here you can see that the wall is white, and here the reflection given by the metal is higher. Well, it's brighter than white. What does it mean? It just means that the wall that is beside is brighter than this wall. Okay, so the question of the color of metallic mirror is something special. It is not like the evaluation of the color of matte material. It is easier to assess the color of metallic mirrors when we have comparisons. Okay, so here we have different metallic surfaces, and can say that this one is yellow in comparison to this one. Okay. Or we can compare the object in the scene and its reflection. See that here the mirror is yellowish because all colors of the scene are yellower the reflection. This was for flat surfaces, but now let's go a step further in the cases where we have concavities. So we have a 3D object, not a convex object, but a concave. Okay. And what happens is this, what Lionel has evocated at the end of his presentation, is the interreflections between the facets. So here we have two small glass plates covered by gold, opaque, so it is like gold mirrors, and we can see the multiple reflections. So here the light source is reflected once, and here we have the reflection of the other plate, and here the reflection of the reflection, and here light is reflected 4 times. And we see that the color of gold is not that pale yellow that we know usually, but it turns to something darker and orange. And this is something that can occur between big glass plates covered by gold in mirrors, but it can also occur at a smaller scale. We are still in the macroscopic model in that presentation. So let's say that it is more than 1 micron, but it is what could occur, for example, in the brushed mirror with big strokes. And the appearance can be an average of what we are seeing here. So this is what I want to detail. So, okay, here we have one concavity, but we can imagine that we have many concavities, one after the other. And if we look from far, we will see the average between all that. Yes, so this is something that we worked on a few years with Dorian Sapin, a PhD student that we co-supervised. And we try to model the multiple reflections of the light in the cavity. And there is a very convenient way to represent that, thanks to the mirror symmetry. Instead of following all these broken paths, we have a straight line with what we call the kaleidoscope. And of course, all the angles are the same in the 2 configurations, but it is much easier to represent it like that. And just by following the line, we see how many times the facets are met. Okay, so here we have 4 reflections. We can, of course, it depends on the position. Here, that ray flows 1, 2, 3, 4 reflections. This one, only 3 reflections. Okay, so depending on the position and the angle of the ray, we have a certain number of reflections. It is not sufficient to model that in 2D because actually you can have oblique rays that are in the direction of the strokes. So it is a 3D model, and we have to pay attention to the polarization. Yeah. Problem of polarization is that, well, as Lionel said, we can choose the direction, the P and S direction, according to the orientation of the ray. So a ray that is reflected like that, we have the wave, the component that oscillates like that. like that. Okay. But the second reflection, so I choose a ray like that. Like this. The problem is that I am not either perpendicular or parallel anymore. I change that configuration. So I need to find the new S and P orientations. So we have the first reflection. We decide which orientation are P and S. Okay, I am reflecting once and I have something oblique and I need to project this component into the new S and P orientation. So we use a rotation matrix. So here it is the reflection of the P and S component. And we rotate to be aligned with the new incidence plane. So we introduce the rotation and we consider the second reflection and so on and so on. So if we have 5 representations, we do reflection or rotation, reflection, rotation, and so on. This is something, it is just geometry, but we need to think in that because it can change many things in the final appearance of the curved surface. And in the end, we have the total reflectance with a formula like that. The question is, how many reflections do we have at most, depending on the shape? So if it is flat, that's easy. Whatever is this angle, the light is reflected once at most. But when we have cavities, consider that we have 120 degrees between the two facets, we can have 1 or 2 reflections. Depends on the position or the incidence angle. So at grazing angle, we have 1 reflection at most, but at normal incidence, we can have 2 reflections. And we have modeled that for different angles. So 45 degrees are very deep. So cavities, and we can have up to 1, 2, 3, 4 reflections in it. And what we have in terms of color, so we model for a given point of view, we model all the possibilities of light reflection, including 1, 2, 3, 4 possible reflections. And if we have already seen the color at the different angles if the surface is flat. But if we have deep cavities, we see that at normal incidence, the gold looks orange. So it is depicted by the fact that the light is more reflected more times. So the reflectance decreases here. And in terms of color, flat is pale yellow and becomes a little darker, more saturated, and more orange. This is something that we can see easily in some well-known objects. And you can see here the reflection, 1 reflection, it is the pale yellow color, but where the light is reflected multiple times, we'll see that a yellow color for gold. Another view. This is something that we have seen with Yonah coming back at the San Francisco airport, coming back from a conference on material appearance. There was an exhibition of tableware, and it was very strange to see that so pronounced orange color, and actually it is just gold in which there were multiple reflections. So another view. But here we are at a more grazing angle, so we have less reflection, so it is a bit less orange. We have similar things with silver. Silver is rather achromatic metal, but in fact it absorbs a little short wavelength, so it is a little yellowish. This is how we can distinguish silver with steel. Steel is really gray, whereas silver is literally yellowish, and that yellowishness increases when we have these cavities, and this is also something that we can see with the wire. Here we have multiple reflections between the plates and the base, and it becomes a little yellower. Again here, you can see also here. And it is not because we have different material from outside and inside. It's just the multiple reflections that are visible. And it is the most striking is with copper, where it turns definitely to red. Okay, so once again, we see that the short wavelength, the light is more and more absorbed when there are more reflections. And this is something that we can see easily from images in the internet. The reflection of the reflection of the reflection turns to something red. You can see it here, also here, and so on. They come to the conclusions by saying that, well, we have understood that metals have a specific appearance due to their optical properties. And when we want to assess the appearance of the metal, the structure, the shape is extremely important to consider, because light is not, most of the time when we consider a material, we assess it with a flat. And this is a problem for many applications. Each time it turns to something curved or something incurved with cavities, well, the appearance changes a lot. This is what I wanted to show through these examples. The difficulty is to model these multiple reflections or the specific reflections when we have a curved or a non-flat object. And usually for this application, ray tracing is the gold standard method to assess that. We have tools to do it today. I thank you for your attention. Is there any question? I turn to my church. No question that? Perfect. Yes.
Thank you very much for that very kind presentation. Do you consider also surfaces that are not only specular, but when roughness is present, the same kind of transportation of light works too?
That is obviously an excellent question, because yes, what happens? Here it is very easy when we have mirrors, and when it is not a mirror, it means that the first rays start to be scattered, and then more scattered and more scattered. Actually, the advantage of that is that we can turn, it is similar to what we call a two-flux model. We have an analytical model with formulas. So in terms of computation, you can have all the angular configuration in seconds or at most a minute. When you need to consider scattering, there is no analytical formula anymore. So it is ray tracing. It is much longer to consider. So we don't have analytical formulas. So yeah, and I am thinking far too far to have something somehow analytical when the faces here are rough, but I couldn't get it yet. So hopefully in a few years, or just use a renderer.
Okay. You need also to consider diffuse lighting, not only directional lighting as you proceed.
That's also something that not insist with, but when you look at metallic objects, if you have only light that comes from one direction, either see the light in the reflection direction or it is black. So of course, a metallic object shows its complete appearance under a diffuse lighting. This is what is assumed here. Whatever your position, you always have light rays that are reflected. We see the specialist of machines.